Welcome to the video lecture for section 5.2. This is for statistics, STA 2023. My name is Jorge Gavillan. So in this section, we're going to be talking about the binomial probability distribution. And so the focus, of course, will be on the binomial probability distribution and how can we find probabilities that pertain to the binomial probability distribution. We're also going to find the mean and the standard deviation for a binomial distribution. And I'm not going to talk a lot about the significantly low or high issues that the textbook loves to talk about. So the first thing is a binomial probability distribution results from a procedure that meets four requirements. So remember when we did a probability distribution, we had three requirements. This one has four. The first one is that there's a fixed number of trials. And so that means, for example, if I were to flip a coin 10 times, that would be the number of trials. That is one single observation, my 10 flips. The trials must be independent, meaning that the outcome of any individual trial doesn't affect the probabilities in the other trials. So in other words, if I flip a coin 10 times, the probability of getting tails is 50% every single time. And then number three, each trial must have all outcomes classified into exactly two categories. Binomial distribution is binary. It's either yes or no. And so they commonly refer to this as success or failure, but the term success and failure are arbitrary. That really has nothing to do with actual success the way that we define it in everyday language. And then the probability of success has to remain the same for all the trials. Again, if I flip a coin 10 times, the probability that I get heads or tails is 50% every single time. It does not change. And so here's some information that we have as far as how we can find the probabilities. We have S and F, success and failure. Then those are two possible categories of all outcomes. If the example for the coin would be H and T. So the probability of S is equal to P, which is the probability of success, and the probability of F would be 1 minus P, which is equal to Q, which is the probability of failure. And then N is the fixed number of trials. So for the example of flipping a coin 10 times, N would be 10, P would be 0.5, and Q would also be 0.5 because it's a 50-50 chance. Now, X is a specific number of successes in N trials. So X can be any whole number between 0 and N. And so going back to the example of flipping the coin 10 times, it will be between 0 and 10 inclusive. And then P is the probability of success in one of the N trials. Q is the probability of failure in one of the N trials. So going back to the flipping the coin, the probability of getting tails would be my success, and the probability of getting heads would be failure in this example. And then P of X is simply the probability of getting exactly X successes among the N trials. And that's why we can use binomial probability to find information such as this. Again, like I said before, the word success is arbitrary, does not represent something good or bad. And so he does, in the textbook, they tell you to caution when you binomial distribution, always be sure that X and P are consistent. In other words, that the number of successful outcomes, if you will, and P are measuring the same thing. And so, but honestly, at this level, they will be the same thing. Maybe at some other situation it wouldn't be, but in this case, they are. They're the same category always. So here's the first example. When an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is. And this is based on a result from a Pew Research Center survey. So suppose that we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is. A, does the procedure result in a binomial distribution? B, if this procedure does result in a binomial distribution, identify the values of N, X, P, and Q. So this procedure does satisfy the requirements. The number of trials is fixed, is 5. The 5 trials are independent because the probability of any adult knowing Twitter is not affected by the results of another adult knowing what Twitter is or not knowing what Twitter is. Each of the 5 trials has 2 categories. Either the person knows what Twitter is or they don't know. For each randomly selected adult, there's a 0.85 probability that this person knows what Twitter is, and the probability remains the same for each of the 5 selected people. So having concluded that the given procedure does result in a binomial distribution, we now proceed to identify the values of N, X, P, and Q. So with 5 randomly selected adults, N is 5. And so we want the probability of exactly 3 who know what Twitter is. So in this case, X is equal to 3. Now, the probability of success is 0.85, so P is equal to 0.85, and the probability of failure is 0.15. Now, remember, P plus Q are always going to be equal to 1. So, again, it's very important to be sure that X and P both refer to the same concept of success. In this case, it does. So, therefore, X and P do use the same concept, knowing what Twitter is. And then here to talk about the 5% guideline, when sampling without replacement and the sample size is no more than 5% of the size of the population, then we can treat the selections as independent. In this case, they are independent because we're doing it with replacement. So the binomial formula is the following. P of x is equal to n factorial divided by x minus n factorial times x factorial times p raised to the x times q raised to the n minus x, for, in this case, x is equal to 0 all the way through n. N is the number of trials, x is the number of successes, p is the probability of success, q is the probability of failure. So in this example, given that there's a 0.585 probability that a random selected adult knows what Twitter is, use the binomial probability to find the probability that when 5 adults are randomly selected, exactly 3 of them know what Twitter is. That is, we're going to apply the previous formula to find p of 3. Given that n is equal to 5, x is 3, p is 0.85, and q is 0.15, we get the following. So the probability of exactly 3 adults knowing what Twitter is 0.138. And so there's a way that we can do this using Excel, and I'm going to show you what that looks like. And so in Excel, we can actually use the formula here, and the formula is binom.dist. And so there are 4 pieces of information that you're going to need when you use Excel to find this probability. The first one is the number of successes, and in this case is 3. The next number is the number of trials, which is 5. The next number is P, which is 0.85. And then the last piece of information, Excel is asking, is this cumulative or not? And it's not cumulative because we only want the number 3. Now, there are times that we want the cumulative, but we don't want it now. So what happens is that we put all that information together and we get the answer, which is 0.138, which is exactly what they got here by not using Excel. Now, so if I wanted to find the probability of 2, I just change the 3 to a 2, and so on and so on. But everything else has to remain the same. Now, here's another example. Based on a Harris poll, 60% of adults believe in the devil, assuming that we randomly select 5 adults. Here it says use the table. We're not going to use the table. We're just going to go ahead and use Excel. So the probability that exactly 3 of the 5 adults believe in the devil, and B, the probability that the number of adults who believe in the devil is at least 2. So using the table here, we get the following, right? The following excerpt from the table shows that when n is 5, p is 0.6, the probability of x is 0.346. So if I use Excel, it's this cell right here. And so again, you can see that number of success I'm looking for is 3, number of trials is 5, the probability of success is 0.6, and it says false, and I get 0.3456, which is exactly what they got here. And so the next example, the phrase at least 2, I'm going to talk about this a little bit. Successes means that the number of success is 2, 3, 4, or 5. So at least 2 is everything from 2 up to the number of trials. So the probability that at least 2 believe in the devil is the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5, which is 0.913. And so using Excel, it's the formula is slightly different. If we have an at least problem, the best formula to use is the binomial.dist.range. And so there are 4 pieces of information. The first one is the number of trials, which is 5. The second piece of information is the probability of success, which is 0.6. The third piece of information is the lower parameter. In this case, it's 2. And then the last piece of information is the upper parameter, which is 5. So remember, the probability of at least 2 is the probability of 2 plus the probability of 3 plus the probability of 4, and then the probability of 5. So you have to sum those up. And so we get 0.913, which is exactly what they got in the PowerPoint example. Now, the next thing we're going to talk about, the last thing here from the PowerPoints is the mean and the standard deviation. So the way that we find mu for the binomial distribution is n times p. The variance sigma square is n times p times q, and then the standard deviation sigma is just the square root of the variance, which is the square root of n times p times q. And so let me show you what that looks like. And so here, the Twitter example, we use the number of trials was 5. And so you can see that 5 times 0.85 gives us 4.25. So what does this mean? That means that if we randomly select 5 adults and ask them if they know what Twitter is, the average number of adults that we're going to get that in fact know what Twitter is 4.25. Obviously, we can't get 0.25. So in this case, what we can say is that if I randomly choose 5 adults, 4 of them are going to say, yes, we know what Twitter is. And the standard deviation here is, again, the square root of n times p times q, which is about we can go to 0.79 or 0.8. And so that's the example there for the Twitter. Now, for adults that know what the devil is, if I randomly select 5 adults and ask them, do they believe in the devil, I'm going to get 3 out of the 5 with a standard deviation of about 1.09 or 1.1. And so that's what, in the context, that's what it means when we find the mean and the standard deviation of a binomial distribution. So the next thing that I want to do is I want to talk about this example, and then we'll wrap up 5.2. So here is the probability that a planted radish seed germinates is 0.8. So a gardener plants 9 seeds. Let x denote the number of radish seeds that successfully germinate. What is the average number of seeds the gardener could expect to germinate? So the first thing is I have some piece of information. I have my n is 9, which is the number of trials. The probability of success is 0.8, which in this context means that the seed will germinate. The probability that the seed won't is 0.2. And so I constructed a probability distribution for this particular example. So since I have 9 trials, out of the 9 seeds that I plant, I can get 0 seeds, 1, 2, 3, all the way up to 9. And that would be my possible trials, if you will. And then so the next thing is that I got the probability for each possibility, right? And so this is my probability distribution. And if I sum this up, I should get 1. And so if you notice here, I got the probability of 0. That means that if I plant 9, the probability that I won't get any of the seeds germinating is 0, basically, right? And you can see the formula that I use. And so the probability of getting 1 seed, again, is very small, close to 0. Probability of getting 2 seeds germinating, only 2 seeds, is again close to 0. The probability of getting only 3 seeds out of the 9 germinating is actually also pretty small. It's about 0.003. And then 4, now they're increasing a little bit more. So this is about 2% that I get 4 seeds, only 4 seeds germinating. Only 5 seeds, about 7%. And then 6 seeds germinating jumps up to about 18%. And then 7 and 8, I get about 30%. And then for 9, I get about 13% or so. And then it adds up to 1 for all of them. And so if I was building a probability distribution for an example, this is exactly how I would do it. The pieces of information that I would need would be the number of trials, the probability of success, the probability of failure, and then I don't have a value there because I built the entire probability distribution, and so I wouldn't need that. And so I have 2 questions here, and the first one is, what is the probability that at most 3 seeds will germinate? So when I say at most 3 seeds will germinate, that means that I'm looking at 0, 1, 2, and 3 seeds. And so there's a difference between at most and at least. At most, you take the number they give you and you go down, and at least you take the number they give you and you go up towards the n, if you will. So what is the probability that most 3 seeds will germinate? Well, there's two ways that I can do this. And if I have at most 3 seeds will germinate, then all I have to do is add up the probability of 0 plus 1 plus probability of 2 and the probability of 3, which in this case gives me 0.003. And so that's one way of doing it. The second way that I can find this information is using the complement. And so I can also do 1 minus the probability of at least 4, and then that will also give me the probability that of at most 3. And you can see here that we have exactly the same values for both of them. So if you build a probability distribution, these types of questions are actually quite easy to answer. Now the next one, number 2, is what's the probability that at least 5 seeds will germinate? So from the previous example, you know that that's the probability of 5, 6, 7, 8, and 9 summed up, right? And so using this table here, I can sum up everything from 5 to 9, and I get my answer, which is about 0.98%, right? About 98% that I will get at least 5 seeds germinated. And there's another way of doing it again, and that's using the binomial distribution range function in Excel. And so those are the two ways that I can find at most and at least. So the first thing is build a probability distribution, and then you can use the first method, which is just the sum of the cells that pertain to the question, or you can use the function distribution range to find the answers for at most or at least. And that's the end of 5.2. Thank you.